Hello everyone. For this video, I'd like to dig a little deeper on the topic of efficiency. And I think the best way to discuss this is by using something that you're already familiar with. So I'm going to base part of the lecture on array lists and linked lists. And maybe you notice that I wrote linked lists here as one word because I plan to use Java's linked list class. It just makes things simpler because I don't want you to care about the code. I just want you to care about the operations. And I know that you probably have never used linked list before, but as I mentioned, in terms of usage, there is a difference between Java array list and Java linked list. They both have get, add, set, remove, and so on. The difference is just on how these methods are implemented, and because they are implemented differently, some of these operations, even though they have the same name, for example add, they will have a different running speed. We have talked about why this is the case, and you know how they are different because you have implemented both array lists and linked lists in the last few weeks. But I will give a quick review of this again in a bit. Now, when we talk about efficiency, it's hard not to mention something called the big O notation. This is just a notation that we use when we want to talk about the efficiency of a program. We're not going to discuss big O notation that deeply, and in fact, you don't have to worry about it for the final exam because we're not going to ask you anything about the big O notation. However, this is something that you may see again in later subjects, depending on your degree, and it's also something that computer programmers are expected to know, so I thought that this is a good opportunity for a gentle introduction. I'm only going to give you an informal introduction, so fairly little mathematics, because I know most computing students are allergic to mathematics, but hopefully it will be enough so that you have an idea of what big O notations are and how you use them. Maybe later on, you can refer back to this video if you ever encounter big O notation in other subjects. Okay, so let's get started. And let's start by talking about array lists and linked lists again. At this point, I hope you remember why you would prefer one over the other. With an array list, it's slow to add something to the start, at least when compared to adding something to the start of a linked list. Do you remember why? This is because an array list uses an array, so every now and then it could be the case that the array is full. And when the array is full and you want to add a new element, for example, I want to add 9 into this array, you would have to make a new array. And then you would have to copy every single element from the old array into the new array, leaving one space at the start where you can put the 9. Now, with the linked list, it's different because if you want to add an element at the start of the linked list, then all you need to do is make that new node, and then you only have to do 2 more operations. You just need to change 2 variables. You have to link the new node to the current start of the linked list, and then you change the start of the linked list to the new node. So here's the thing. It doesn't matter if you have 10 nodes or 10 million nodes in your linked list. It will take the same amount of time to add a new node at the start because you will always only have to do 2 operations. But with an array list, it's different because if you have 10 million elements when the array is full, then you will have to move that 10 million elements to the new array. Now, we can actually see this happening in Java. I'm going to show you a simple way to measure the running speed of a program in Java. You can actually ask Java to give you the current clock time with the command system.currentTime_millis. Well, this is actually the number of milliseconds from January 1st, 1970, which has some historical significance, but don't worry about that. All you care is that if you run that command, and I'm just going to print it out here, you're going to see a big number. This is the number of milliseconds from that date I mentioned. So if you run a few times, it will keep on increasing because, well, it goes up with time. So if you want to measure the speed of a program, or just a method, or even just a loop, all you have to do is set the start time somewhere. So I'm gonna copy the start time here, and then I'm going to put the end time at the bottom. So long here is a variable type that can store a very large integer, because as you can see, this is a pretty big integer. And that's it. We can probably run something in the middle. Let's have a simple loop. Let's run it 1,000,000 times. Let's just count something. Okay. So what I do is I take the time, I record the time at the start of the loop, and then a record time at the end of the loop. And then I'm just gonna print out the difference. So let's write that down. And run it. So this loop only takes 1 millisecond to run. And even if I make it much bigger, let's say put it 1 billion, I don't think it will run that much longer. Okay, we went to, well, on average is about still just 1 point something millisecond. Now we want to compare the operations of a linked list with that of an array list. So let's add our array list and linked list. I'm going to call our array list R and our linked list list. Right now they're both empty, and I don't want to write a loop that keeps on adding an element because that can be slow actually. So what I'll do is I'll make an array, let's call it base, with 10 million elements, which is now filled with 0. And then I will use base as an argument for both the constructor of array list and the linked list. So you probably have seen Gaurav done this before. Basically, I'm converting the array into an array list and also a linked list here. They should now both have 10 million elements. Okay, so let's now write that in. Obviously, you're going to need to import java.util.star to have access to both array lists and linked lists, and also arrays. That will let me convert from the array into an array list and linked list. And just to show you that this array list and linked list do have 10 million elements each, let's try to print out the size of these containers. List.size and r.size. Okay, running both. You see they both have 10 million elements. Okay, so far so good. Now what I'm going to do is I'm going to start with the linked list. In fact, what I'm going to do is I'm going to just say long start and end here, so I don't have to declare up down here. I don't need that. So I'm just going to add an element to the linked list. So list.add, we can add a start, so we can add index 0, we can add 1000 and see how long that takes. Well, it takes 0 millisecond. And what if we do it on the array list? It takes 39 milliseconds. I'm going to run this a few more times so you can see how long it takes on average. Or maybe better yet, what we can do is we can write a for loop that will do this 5 times, say. Let's say 5 plus plus. So now you see that, oh. So it's taking 34 millisecond first one, then it takes only 10 millisecond on average for the next 4. Can you explain this behavior? My guess is that the first operation takes longer because Java has to make a new array and copy every element from the old array into the new array. But the next few operations are faster because you only have to move elements in the array because there's enough space, right? You just shift everything to the right by 1. So Java doesn't need to make a new array very often because I think the new array is about 50% bigger. So I think if we increase the number of insertions, so let's say 20, I don't think you will see an increase in the insertion time for this. Yes. So as you can see here, only the first insertion takes a bit of time. Okay. What about if we add to a linked list? Let's change that into list. And it takes 0 milliseconds for all of them. And what's even more, I'm going to increase the size of the array list, well, linked list and array list both, to let's say 20 million. Does it make any difference? Nope. To 30 million. Doesn't make any difference. Nope. It's taken longer and longer to start because it needs to copy the base array into the array list and linked list. Now let's change that into, let's change this back to array list. start at 10 million again. I'm just going to reduce I down to 5 because we don't need all these numbers, right? Okay, so let's try 10 million again. Takes us 42 milliseconds roughly. I'm going to increase that to 20 million. Takes about 60 milliseconds. Let's run a few more times. 60, 63, 61. Let's change that to 30 million. Run again. I'm getting 95 milliseconds. Run it one more time. So when it was 10 million, it took us about 30 milliseconds. Well, 30 to 40. When it was 20 million, took us about 60 milliseconds. When it got to 30 million, took us about 90 milliseconds. So I guess if I put in 40 million, oops, it's going to take us about 120 milliseconds. 142, a bit longer, but pretty close. So let's change that to 50 million. Hopefully we get about 150, 160 milliseconds. 165, close enough. Okay. In fact, I did a bit of experiment and these are the numbers that I got. So the increase is quite consistent. If you double the size of the array, you double the time it takes. If you triple the size, you triple the time that it takes, and so on. So going from 10 million to 50 million, it's pretty close to about a 5 times increase, right? And for the linked list, it's also pretty consistent because it always takes 0 millisecond. And we know why, because you will only ever need 2 operations. So it doesn't matter how big the linked list is, you'll always take the same amount of time, which is almost nothing. And the cool thing now is that we can probably guess how long it will take if we keep on increasing the number of elements. And that's good news because we don't have to run the experiment for 100 million, 200 million, and so on, because that will take more and more time. So if I run add on an array list of size 100 million, I'm going to guess that it'll take about 300 milliseconds or maybe 350 milliseconds. Now, unfortunately, measuring a program speed like this is not very reliable because you saw yourself, there were big variations, right? For example, with 50 million, I was getting 150 milliseconds, 160, 180, because what my computer was doing in the background affect the running time. Or maybe Eclipse has a bit of hiccup, and 10 to 20 milliseconds is a very short amount of time. You definitely can't run a code just once and say, yep, that's the running time. So I went further from 60 million to 100 million. And the good news is it's still kind of increasing. But I can't explain why 50 million is close to 60 million. And this is after running a few times, mind you. I can't explain why 90 million and 100 million, why is 90 million faster than 80 million? Why 100 million takes 4 seconds? I have no idea. What did we predict? 300 milliseconds? Well, we're a bit off. That didn't happen. But 80 million is still pretty close. Like if you multiply 30 by 8, you get about 240. Okay. So not all bad news. And the important point is that for ArrayList add, the time it takes to finish increases linearly with the number of elements in the array list, for the most part anyway. Let's just talk about 10 million to 50 million. In this list here, and I massage the number a little bit, when I have 10 million elements in the array list, it takes about 33 milliseconds for the first insert and 9 milliseconds for the second one. If I have 20 million elements, it takes about 66 and 18, which is double the time. And if I have 50 million, it takes about 165 and 45, which is 5 times the time. And we know why. Because every time we add an element at the start of the array list, we have to move every element in the array list. So if I have 10 million elements, then when I want to add something, I have to make a big array, and then I move 10 million elements. If I have 20 million elements and I want to add something, I have to make an array which is bigger, and then I have to move 20 million elements. So it makes sense that it will take twice the amount of time. If I have 30 million elements, it will take 3 times as long. This all makes sense because the number of elements that you have to move increases with the same amount, right? You have to double the time because you have double the elements. You have to triple the time because you have to triple the elements. So if I have 100 million elements, I can expect it to take 300 milliseconds. Of course, that didn't happen because I don't know. I don't know what Java or Eclipse was doing in the background, but it was a reasonable thing to do. It's just that measuring speed like this is not very reliable. Plus, something I should mention, if I'm running on a faster computer or a slower computer, then the times will be different anyway. It is useless to say that my program runs in less than 10 milliseconds. Why? Because maybe in your computer, but that won't be true on my 10-year-old laptop, for example, right? What about removing from the start of the array list? Well, it is also slow to remove the first element of an array list because you also have to move every other element of the array list to the left. But for a linked list, again, it doesn't matter because you just change the reference from the head of the linked list. So you basically skip the first node, right? So let's give this a try. Let's see if what we think gonna happen is actually going to happen. So I have here almost the exact same code. The only difference is that instead of calling add, I'm going to call remove. And I'm just going to do 5 times. So we'll see 5 different numbers here. Maybe we'll start with 10 million with linked list removal. Let's see how long this takes. Gonna run it once. Okay. 0 millisecond. All right, change that to 20 million. 0 millisecond. Let's just try 100 million. Let's see how long that takes. It's taking some time. Again, because it's making the array list and the linked list. There you go. It still takes 0 millisecond. Because again, when you remove something from the start of the linked list, you only have to do 2 operations. Or maybe just 1. I'm not sure. I can't remember. Right? So now let's try it out for array list. There. Let's start with 10 million. All right, about 9 to 10 milliseconds. Let's try 20 million. Oh, about 14 to 20. 30 million. Are we going to get about 30? All right, between 20 and 29, 40 million. Right, about 40, 50 million. This is a bit strange, but I would say it's about 50. Let's try one more time. Again, the variation is so hard to control because I don't know how Java or Eclipse work exactly. I'm going to try 100 million now, and let's hope it'll take about 100 milliseconds for each. Well, close enough. Again, there's a bit of variation here. So I put the numbers of my experiments here, and the cool thing is that, do you see how the time it takes for one removal is pretty much the same with the time it takes to do the second insertion? Remember, when we were doing add, the first one always takes longer because you have to make a new array. And well, that's my guess anyway. But the second time, it doesn't take as long because you already have a big array, you just have to move the elements. And whether you add from the start or you remove from the start, you're moving the same number of elements. It's just the direction that changes. So it kind of makes sense if the time it takes are almost exactly the same. Let's talk about one more operation now because we've been beating on array lists. So now it's time to show that linked list can be bad as well. Maybe you remember that I always mentioned that arrays are simple, but it's incredibly fast. So doing the square bracket thing should take 0 millisecond, no matter what the index is. That's how fast it is. That's how array works. You will learn more about this if you take COMP1010. But for now, just believe me that this operation is very, very fast. And that is why we still use array for most things. And when you call get from an array list, you just return the element on the index, right, from the array. So that should be very fast as well. On the other hand, with a linked list, you have to move the pointer to the element. So if index is equal to 10, you have to move 10 times. If index is 100, you have to move 100 times, and so on. So you expect the get operation to be slower and slower as the index increases. So let's see if this is the case. Let's bring Eclipse in again. We're going to get the first element from the array. Let's do it 5 times. So the code is exactly the same still. It's just that now I'm doing get. Let's run this 5 times. Yep, 0 millisecond. I'm going to change that into, let's say, 5 million. It takes 0 millisecond. How about 10 million? Well, I can't do 10 million, so I guess I'll do 9 million. 0 millisecond. All right, so let's try list. I'm going to get the first element. Well, 0 millisecond, as expected. Let's go to, let's say 10,000. Let's see how long this takes. Oh, so 0 milliseconds. So I'm going to increase that to 1 million. Okay, it takes about 5 to 10. Not really sure. I'm guessing, let's say about 7. Now, if I do 2, how long should it take? Oh, about 13, 14. Let's do 3 million. Am I getting about 21? Let's get about 14, 13. Well, the variance is hard to control, like we always say. So, but it's about 3 times as long as 1 million. Well, maybe not 3 times as long, but should I get about 30 something here? No, yep. Well, they're about the same. How about we try 9 million? Or 999. Let's try to get the last element. Why is it 0 millisecond? Okay, let's try 9 million. Oh, it takes 3 milliseconds compared to 1 million. It's kind of strange that doing this, using 1 million and 9 billion kind of give you the same answer, roughly. Why is that? Well, I'm not going to tell you why. I think if you've been watching the previous lecture videos, you can guess why this is the case. But for now, I'm just going to argue that the time it takes also increase linearly or almost linearly. You can see it goes up to 4 million. It goes up to, sorry, it goes up to 17 milliseconds, and then it will kind of drop from this point on, is my guess. Yep. So I'll try to discuss this in the next video, but there is an explanation for this behavior. Okay, but anyway, you can kind of see that get does also increase linearly or almost linearly as the size of the index increases, at least for the case of linked lists. Now, this video is getting a bit too long, so I'm going to cut it here. But here's the main takeaway that I want you to understand for the second video. We tried 3 operations on array lists and linked lists, and we noticed the following. If we add or remove an element from the start of an array list, the amount of time it takes increases linearly with the size of the array list. And you can explain why this is the case. You know it. It's because we have to move everything in the array list. Similarly, if we call get on a linked list, then the amount of time it takes also increases linearly, but this time not with the size of linked list, but with the size of index, the input. So there's a difference, and I hope you caught that I didn't actually change the size of the linked list on the last experiment. On the other hand, if we call get on the array list, the time it takes never changes. In other words, it's a constant. It's a very short amount of time, like somewhere around 0 millisecond. And that's the same thing when we're adding an element to the start of the linked list, or when we remove something from the start of the linked list. So these words, linear and constant, are the two words that I need you to remember for the next video. What about the other operations? What if you add to the end of the array list? What if you remove from the end? What if you remove from the end of linked list? These are the things you can experiment with yourself, but you also know how linked lists work. You also know how array lists work. So I think you can figure them out yourself anyway. So give it a go, try the experiment, and see if the result matches what you expect. All right, so as I said, the video is getting too long, so I'm going to stop it here, and we'll pick it up in the next one. All right, thank you.